I want to introduce today's session, Broadcasting Your Attack, Security Testing DAB Radio in Cars. May I present the real Andy Davis.
Thank you very much. Okay, good afternoon, everyone. Hopefully you've all digested your lunch. This is a great slot when everyone falls asleep, but hopefully I'll be able to keep you awake. We're going to be talking about DAB radio. Bit of an agenda first. I'll talk a bit about myself, why I'm interested in DAB radio. We're going to talk quite a lot of DAB theory at the beginning because it's important to understand the context of some of the potential vulnerabilities in the protocol. A bit about how we broadcast DAB, the attack surface, then how I went about creating the security testing tool that I'm going to demo. They give you a live demo of broadcasting DAB radio. We'll then work through a number of example vulnerabilities and then talk about what the implications of these type of vulnerabilities in vehicles are. Now, one thing before I get started that's important to point out, this talk is all about the development of a security testing tool and the capability that it provides to identify vulnerabilities in DAB radios. I'm not going to be talking about specific vendors and specific bugs in specific vendors' products. So there are screenshots throughout the talk of different head units from vehicles. The fact that they are in those screenshots is not implying that there are particular vulnerabilities in those particular head units. It's just we've got a range of head units and those we used for the photographs. So let's kick off. So I'm Andy Davis, I'm Research Director at NCC Group. I'm in a very privileged position to be a technical hands-on Research Director, so I get to play with cool stuff like this. NCC Group, if you haven't heard of us, we're a global cybersecurity assurance specialist. My own personal interests that I pursue in my research are primarily wired and wireless interface security, and more over the last couple of years I've been looking at software-defined radio and how it can be used in a security context. You may have seen some of the previous research I presented at Black Hats and DEF CONs and CANSEC, including some USB testing stuff, some HDMI, VGA testing tools, and earlier this year at CANSEC West, the RF testing methodology for using software-defined radio in security testing and research. So why am I interested in DAB? Well, at NCC Group, we've been involved in security testing vehicles for a couple of years now. And whenever we talk about security vulnerabilities in vehicle systems, certainly to some of our customers, OEMs, tier ones, they always ask the same question: can you remotely attack vehicles based on the protocols that are available in the modern connected car? And when people look at the kind of remote attack surface of a vehicle, traditionally they've focused on at a short range, Wi-Fi and Bluetooth, and then over the long range, the mobile network connectivity via GSM. No one to date seems to have focused on DAB radio, which is interesting. It may well be because DAB is only prevalent in certain areas of the world. It certainly is in the UK and in parts of Europe. But as virtually all modern vehicles that roll off the production line, certainly that get shipped in the UK, come factory fitted with DAB radios, it seemed an obvious area of research to investigate. And as I'll go into in a lot more detail later on in the talk, often the head units that contain the radios, which are also called infotainment systems, you may have heard that term. I'll interchangeably use the term head unit and infotainment system throughout the talk. But often these are also connected to vehicle networks like the CAN bus that allow protocols, data protocols, to communicate with cyber-physical systems like braking and steering, that kind of thing. And as I mentioned, it doesn't appear to have attracted very much attention from the security research community. And also, software-defined radios, which you can use to perform this type of testing, are getting cheaper and cheaper. And you may well have seen a lot of the talks at Black Hat this year have some kind of component with software-defined radio. They're getting more and more common as a research tool. So a bit of an overview of DAB. It was designed as a digital radio technology, so it's primarily for broadcasting audio and as a replacement for FM that we're all used to using. It was originally called Eureka 147, which is a European project many, many years ago. So it was actually launched first in 1995 in Norway. I was quite surprised to find out how long the technology has actually been around. Because it's only really started being deployed in vehicles, in all modern vehicles over the last few years. There was an upgrade to the original DAB standard in 2007, which is called DAB+, and the benefits of upgrading to DAB+ was it allowed for greater error checking within the protocol and therefore allowed for better quality audio. Unfortunately, they are not interoperable as protocols, although you can have a DAB and a DAB+ station running alongside each other in a group of stations, which is known as an ensemble. But I'll come to that in a bit more detail in a minute. So the primary benefits over FM are better signal quality. Many more different services can be sent over FM. And one of those services is called Electronic Program Guide, which is similar to what you see on your TV, modern TV systems. So your set-top box or satellite receiver, where you can see the programs up to a week ahead and set things to record, that kind of stuff. So that's all supported by the DAB protocol. So first of all, we're going to dive into modulation and transmission. If you're still digesting your lunch and falling a bit asleep during this bit, don't worry too much, because when I've talked through how it all works, I'm going to explain why you don't need to know this. But I did decide that I was going to cover it for completeness, because I'm sure there's plenty of people who want to know how DAB is actually transmitted. So the reason that they decided to implement DAB over FM is FM suffers from interference called multipath, which is where you get reflections off buildings and reflections off other objects, and you get interference because the same signal is received at different times as a result of bouncing off these objects. And DAB, in order to cope with this interference, uses a technique known as orthogonal frequency division multiplexing, OFDM. So essentially what you do is you have a whole range of carriers, in fact just over 1,500 carriers, which are all spaced very closely within the bandwidth. And each of those carriers sends a very small data rate. It's actually a bit more complicated than OFDM. It's coded OFDM, or COFDM, because it includes forward error correction to ensure that there's better quality signal. And the modulation scheme that's used within this multiplexing approach is QPSK, which is quadrature phase shift keying. And as you can see in that diagram we've got there, it allows for 4 different symbols, 0, 0, 0, 1, 1, 0, and 1, 1, to be represented by 4 different phases in the way that the modulation scheme is set up. So the audio signals that are produced are digitized, because as I said, it's a digital broadcast mechanism, and multiplexed together with various other data services. So although it's primarily sending audio, there are lots of other data services that you can send over DAB, which is what makes it interesting, and we'll go into the details of the other digital services that you can send later. But essentially, they're all multiplexed together, and this forward error protection is applied to it by adding some redundant bits. For each consecutive symbol, the bits are divided into those 1,536 pairs, which are encoded differentially, so based on the previous symbol. And then each of those differentially encoded pairs of bits are used to define the phase of that QPSK carrier. So like I showed in that the phase diagram, those are the bit pairs, and you specify the different phase for each of those within the modulation scheme. So that all of that together forms 1,536 carriers in a large kind of wide bandwidth. And that process is repeated again and again, symbol by symbol. So just to explain, as a result of that, as a result of having lots and lots of different carriers that are all very low bandwidth, you end up with a total bandwidth of just over 1 megabit a second. Now, I talked about multiplexing and the fact that you've got these different audio and digital data services that need to be multiplexed together. They are multiplexed in something called the main service channel. And as we'll go through this, you'll see that DAB is a horribly complex protocol, and there's lots and lots to it. I'm just scraping the surface here with some of this stuff. I could probably spend all day talking about the protocol spec, but I'm not going to. Talk about the stuff that's important. So it is important that we go through these bits first. So you've got this thing called the main service channel, which is 55,000 roughly bits in our what are known as common interleaved frames. Okay, so each of those frames is divided into time slots, and you have these things called sub-channels, which are repetitive bursts, and the data for each of these CIFs is transmitted in 18 consecutive symbol blocks. Okay, so the first of those is used for synchronization, and the remaining contain useful information for the receiver. So you've got the multiplex configuration information, all the information about what's in that multiplex, so the types of data, the names of the ensemble, which is the collection of channels, and all kinds of kind of configuration information. And it also contains this thing called the fast information channel. And there's a bunch of other channels that are used for synchronization and housekeeping. So typically, when you have a DAB transmitter, you have two separate components, hardware components. You'll have the multiplexer, and that will be connected to the modulator and transmitter. And the interface between those two is called the ensemble transport interface. And the reason that they're separated is quite often in a broadcast scenario, those two hardware components may actually be in different physical locations. So the ETI transport is actually sent over an E1 line. It's a 2 megabit synchronous data stream line. And if any of you are aware of data transmission protocols, it's a pretty standard protocol for transmitting 2 megabit synchronous data. There's a an ETSI standard associated with how this is all formed, and there's an open source tool called Ettisnoop that allows you to actually look at this stuff. So within that fast information channel, which is the first kind of layer of multiplex data, I'm going to kind of drill down and explain that we need to go through this to get to the bits that are useful for security testing. So the purpose of the fast information channel is when you first turn on your DAB radio, it needs to know specific bits of information to be able to tune in and be able to present you with the services that are available. So this channel is divided up into what are known as fast information blocks, and each fast information block contains a number of fast information groups. So these screenshots that I've got are taken from the standard, and the standards are large and complex. And that's important because when I come to talking about potential vulnerabilities, the complexity is key. So there are numbers associated with these fast information groups, which represent the type of them. So, for example, some of them are for labels. Now, labels are things like when you tune to a channel on your DAB radio and it tells you the ensemble name, so the group of channels. So in the UK, one of the ensembles is National One, which has got all the BBC radio stations in there. But the label is the name of the ensemble and the name of each of those radio stations within the ensemble. So you'll have figs that represent those labels and other that represent other configuration information. And just to make it even more complicated, you delve down a bit deeper. So each fig type has a whole bunch of extensions which provide specific services. Service information, SI. So basically each of these fig extensions is like a function, a service function. So the service information features, which are signaled using those different fig types, there's a few of them to just demonstrate the kinds of things that they're used for. Service linking information, for example, is a function, and that is where if you're driving in your car and you're listening to a radio station and the audio associated with that radio station, as you move into a different geographic location, is provided on a different frequency, your radio will have a database of information associated with, well, it will basically know that as you move out of one region into another to seamlessly transfer over to the different frequencies so that you're getting the correct audio stream, and you don't notice the fact that the signal drops and then picks up again. So that's service linking. There's lots and lots of these, providing lots of different functionality within the underlying protocol. And as we'll see as we go on, some of them have the potential for introducing security vulnerabilities. Another one worth mentioning there actually is the transmitter identification information database. It's another database that gets downloaded to the receiver in your car with physical geolocation information of the transmitters. So another kind of large blob of data that's getting sent to your receiver to be processed. Now, user application information, which is one of these FIG extensions, is where I started thinking, oh, this looks quite interesting. This is something that, I can see some definite potential for security vulnerabilities here. And that's the fact that within DAB, you're able to transmit a whole bunch of different protocols over the top of it. So it can be the carrier for example, slideshow. Now, MOT is multimedia object transport, which is yet another protocol for which there's yet another complicated spec that explains how it's encoded. But essentially, your MOT data is fed into your multiplex along with the audio that you're transmitting. And MOT Slideshow allows you to send PNGs and JPEGs over DAB. And that's typically used for album artwork, for example, in conjunction with the song that's being played, or maybe a photograph of the current DJ that's on air. So that's pretty interesting. But then you've got other things like MOT Broadcast Website, yet another spec that you can download. And what Broadcast Website does, and by the way, that typo's directly lifted from the spec. It's not mine. Broadcast Website, what it does is your radio in your car, your head unit, is provided with a collection of websites that are downloaded, and you can then locally browse to those web pages on the head unit. But it's all part of the DAB spec. What else have we got? Electronic Program Guide, yet another protocol. Java, so you've got the ability to send Java applications over DAB. Even video. Does it say video on there somewhere? Yeah. So lots and lots of interesting stuff that you can send over the top of it. Program-associated data is something that's within the main DAB spec, and it's something that you'll have definitely encountered if you've used a DAB radio. It enables you to send data that's directly associated with the current audio stream. So, for example, you will regularly see the name of the current track that's being played on the receiver, and that's sent as program-associated data because it's synchronized to what you're listening to. In fact, that DAB slideshow as well is program-associated data in the way that it's transmitted. And that's the data that you see that's presented on the screen, that's like the current track, or maybe information about the current station that you're listening to, is sent in what's known as DLS, Dynamic Label Segment. And within DLS, you can send any text you like in a whole bunch of different international character sets, and it gets rendered by the head unit and displayed to the user. Okay, so you've probably got the idea about DAB theory now, so we won't go into any more spec stuff. Well, not too much detail anyway. So a very simple DAB transmitter, as I mentioned, you have this box, the multiplexer, which takes in the information that's data and audio, multiplexes it together to form this ensemble template interface, sent into the modulator, and then transmitted. In this case, it's going to be transmitted using a software-defined radio. So how do we go about broadcasting DAB? All of that stuff at the beginning sounded pretty complicated, and it is pretty complicated. And fortunately for us, all the hard work's already been done, because the guys at opendigitalradio.org have actually implemented all the hard stuff in an open source DAB transmitter. So using ODR DAB MUX, we can multiplex up the signals that we provide it, and that then connects into ODR DAB mod, which will communicate with the SDR and actually transmit our DAB radio. There's also an extra component, FDK AAC DAB+, And what that allows you to do is leverage the functionality of DAB+, which will transmit in the higher quality audio, which is AAC. That's the audio protocol that's used with DAB+. With traditional DAB, it uses MP2 for audio encoding. The software-defined radio we're using is in a SERP B200, which is a pretty flexible tool. I've seen quite a few of them at Black Hat and other talks. Costs around about 650, 700 US dollars, I think. And one thing that's really worth mentioning at this point is legal considerations. Now, obviously, you don't want to be broadcasting DAB radio to air, especially if it's high power and you're going to in any way affect the legitimate DAB radio signals. It's against the law and it's obviously very irresponsible. So during the research, I confined myself to transmitting via a cable to whatever receiver I was connected to, rather than actually transmitting to air. There were a couple of situations where I did transmit to air within a Faraday cage, so we've got some small Faraday cages at work, and but most of the time what I'm using is an attenuator, which I'm connect to the transmit port on the SDR, and the attenuator reduces the signal level to emulate the signal path through the air, so I can physically connect the transmitter to the receiver and not worry about actually broadcasting anything illegally. So what about the DAB attack surface? I've kind of hinted at various bits and pieces along the way about where there may be potential security vulnerabilities. The FIG data within the ETI, because of its sheer complexity, needs to be parsed and processed by the receiver. So manipulating that and crafting elements of that to try and generate memory corruption vulnerabilities in the receiver in the parser software is an obvious place to start. Similarly, with some of the other protocols that work alongside the kind of underlying DAB protocol, like MOT, the multimedia object transfer, being able to manipulate and specially craft elements of header data within that protocol can potentially trigger security vulnerabilities through memory corruption bugs. Looking at the DLS and DAB labels that I mentioned, those get rendered by the head unit and displayed. Now, a lot of these modern infotainment systems will render text in different ways, and depending on how that text is being processed, as I'm sure a lot of you will be aware of, when you're rendering a data stream, there's a whole range of potential vulnerabilities there, from things like secret injection bugs to format string bugs, all those kind of things. So that's obviously an interesting area to look at. And of course, you've got your audio stream, your images, potentially video streams, apps, Java apps. You can send raw data and IP data over there as well. So there's lots and lots of things that you could potentially send that would need to get parsed and processed by the receiver and could trigger security vulnerabilities. So how do we create the security testing tool? So what we did is we took these open source products and added kind of hooks into them that allowed us to manipulate the data along the way. There's a tool called MOT Encoder, which actually understands and produces MOT encoded data that's provided to the multiplex. And what we can do is we can provide DLS data and slideshow data to the MOT encoder program via a FIFO. It gets consumed by that and added into the multiplex, and that then allows the MOT data, so the DLS and slideshow information to be sent over DAB. So we manipulated, or modified rather, the MOT encoder tool so that we're sending the data off via a TCP socket to a separate process. The tool's written in Python, and it's basically man-in-the-middling the data and manipulating the MOT protocol on the fly before the data's then sent on to the multiplexer. And the ODR DAB-MUX open source product was modified in a similar way. At the appropriate point within the software, the data stream was siphoned off via a TCP socket to a separate manipulator that modified that data based on a whole bunch of fuzz cases. So the fuzzer, which is called Dabble, enables you to fuzz DLS data. So, you know, this kind of text-based stuff that's rendered by the head unit. It allows you to fuzz JPEGs and PNGs, again via a FIFO. You can fuzz the MOT protocol and the ensemble data as a result of the hooks that we put into the open source product. There's a bunch of planned capabilities as well that we want to add. So with the open source ODR DAB-MUX, it doesn't support all of the functionality of DAB. So there's a whole bunch of extra elements of the protocol that we could add into there for support. And also, you know, sort of as well as the protocols that could be sent over it, the underlying DAB protocols, some of those aren't currently supported. So the intention is to add that capability as well. So here's a screenshot of the SDR, which is in that black box, transmitting DAB signal via that wire into the back of that head unit. And there's a high-level picture of the connectivity between the different components. So if we think back to the original diagram of our transmitter, where we had our multiplexer and a modulator, now we've got the fuzzer sending the data streams for DLS and SLS's slideshow into the MOT encoder. So you can either just manipulate those particular protocols, so send lots and lots of images or send lots and lots of specially crafted DLS text data, or you can manipulate the actual underlying protocol that's being used to add that into the multiplex. So let's see if we can do a demo. Now, I'm not going to demo it fuzzing, because watching a fuzzer running is like watching paint dry. But I'll just give you an example of me transmitting something. Now, because I've got an extended screen rather than a duplicated screen, hopefully I'm seeing the same as what you're seeing. But just to give you an example of the way that the ODR DAB-MUX is set up and configured. You can see within this simple configuration file that you set up an ensemble, you set up services within the ensemble, channels and sub-channels. And you know, I mentioned labels earlier. There's within the protocol, the way that the labels are encoded, you can see that you specify the labels associated with services and ensembles within this text file. Now, if I switch back to here. Okay. Now, what we've got here is the laptop that you're looking at the screen at is running a DAB receiver. So this is an open source free DAB receiver. And it's using an RTL SDR dongle, which is plugged in here. And that's connected via a physical cable to the transmit output of this SDR that I've got here. So I'm basically going to be transmitting from the usurp radio via the cable, which is emulating the signal path over the air, because I don't want to be transmitting RF in here, to the receiver, which you're looking at on the screen there. So if I start it up, hopefully. Right, so you can see there that we're actually receiving a signal now. So it's receiving a radio signal called security testing with an ensemble called NCC. If I just turn up the audio, listen to what's playing. That's the audio being broadcast. Now, I mentioned DLS information, so if I want to send some DLS data, hopefully it should appear in this box here. Hello, Black Cat. Okay, so it's, oh, and here comes an image. So this is using the slideshow protocol to send image data. Nearly there. Okay, so you can see there's a JPEG image that I sent via the DAB transmission over the air. Now, obviously, it took a little while to transmit that, and if you're going to be fuzzing, that's going to take a heck of a long time. You can, with the images that we've been using for our fuzzing, they're actually tiny, tiny JPEGs, which take a split second to send over the air. But I mean, it's still quite slow. Ideally, if you were fuzzing a real head unit, what you'd want to do is you'd want to identify what the image processing library was through reverse engineering the firmware, fuzz it offline, and then demo it using a proof of concept using this technique to send it over the air to demonstrate that the attack would work via DAB. And as you can see with the DLS data, in this instance, it's literally just printing the text. It's not rendering it in any particularly clever way. But on some of the head units that we've looked at, they are a bit more creative about the way that they're rendering that. And it's generated all kinds of unusual results with the way that, ooh, who's that? Rick Astley makes an appearance. He gets everywhere. So with DLS data, you can send SQL injection, cross-site scripting, because a lot of these head units are connected to the internet, remember, these days. And it's generated lots of interesting results. Right, let's get back to this. So some example DAB vulnerabilities. I've mentioned the MOT slideshow. JPEGs, PNGs need to be rendered by the receiver. There have been plenty of documented vulnerabilities in image processing and parsing libraries. Many of these head units are running operating systems like QNX and Linux and using open source image parsing libraries to process this slideshow data when it gets rendered on the screen. I mentioned about the ensemble label and pad data. Buffer overflows are pretty unlikely associated with DLS data because there is a hard limit, a fixed limit within the protocol, and you cannot physically transmit more than a certain number of characters. However, there is the definite possibility of things like format string bugs when data is being stored off or the way that it's physically being printed to the screen using insecure functions like printf and sprintf, that kind of thing. A lot of the head units we've looked at implement SQLite. So there's the potential of SQL injection in some scenarios. Certainly if the head unit is storing the list of the radio stations, the DAB stations and ensemble names that you've tuned to. So if they're getting stored off in a database and you provide a label which contains SQL, there's the possibility of SQL injection that way. And I mentioned about the fact that some of the head units are connected to the internet, so there's the possibility of cross-site scripting. Databases of information. I talked about service linking at the beginning and also transmitter identification information. These are both databases of information that get downloaded and stored within memory regions on the head unit. There is certainly the potential for buffer overflows in this scenario where fixed size memory areas have been allocated to download these. They are supposed to always be the same size, but of course, if we've got the ability to manipulate that data, the developers shouldn't have made assumptions about the size of the data that might actually get supplied to them. Now, the implications for other vehicle systems. When I've been talking to people about this research, they will say, yeah, but, okay, you gain access to the infotainment system. What can you then do? Surely it's not actually connected to any other vehicle systems. Well, it's actually amazed us, the number of different architectures you see in vehicles and the different ways that these head units have been designed to integrate with other networks within the vehicle. So we've seen situations where the CAN bus is directly connected to the head unit. We've seen situations where you go via D-bus to connect to the CAN network. D-bus, on one particular example of a vulnerability that we found on a head unit, we actually managed to gain access to it via a Wi-Fi attack, but D-bus was bound to all the network interfaces and therefore accessible via Wi-Fi. And because of the way that the head unit had been designed, they wanted to enable the user to be able to turn on and off the ADAS functionality. Now, ADAS is Advanced Driver Assistance Systems. So this is things like advanced electronic braking, advanced emergency braking, adaptive cruise control, lane keep assist, blind spot monitoring. So if you as a driver have enabled advanced emergency braking, which essentially looks to see whether you're with a safe distance of an object in front of you, and somebody can connect via a wireless vulnerability like DAB, for example, and they can then send a direct D-bus message from that infotainment system to disable one of these ADAS features. That's pretty serious, and that's something that we've seen in the real world. The fact that DAB is broadcast, obviously there's the prospect of attacking many vulnerable vehicles simultaneously. So you could have two different scenarios here. One where the attacker uses a very high power transmitter to overpower a signal that's already there. So if you know that everybody's tuned into a popular radio station, you can overpower that with a very high power transmitter. So that as they get into range of your transmission, their radio is going to start picking up your signals. That's obviously not very stealthy, and it would get picked up very, very quickly by the authorities. A much stealthier way of doing it would be to use a low-power transmitter, use a completely new radio station on a frequency that's currently unused, and choose your radio station to entice your target audience to tune in. And most modern DAB receivers are constantly retuning to look for new stations. So it would spot yours and present it to the user to tune in. So just some conclusions. DAB is an obvious remote attack route into a vehicle that hasn't been investigated prior to this research, not publicly anyway. Using a single attack, you could broadcast to many targets. There are lots and lots of different protocols that you can send over the top of DAB, which could be attacked. And the core DAB protocols can also be attacked. And as a final thought, how many DAB radio developers have made the assumption that the broadcast data is to be trusted? There's some bedtime reading for you. Thank you very much. Does anybody have any questions? Yeah, there's a question over there. Sorry? That one? Could you use the microphone? I can hear it.
Is the way to disable DAB radio if you had a newer car?
It's pretty integrated in modern vehicles. I mean, if DAB is one of the services that's being offered within your region, so for example, in the UK, all the modern vehicles have got DAB on by default. I don't think as an individual user you could disable that feature within your infotainment system. I mean,
Okay.
you could decide not to listen to the radio.
And that would disable it?
Well, if you're not tuned into a radio station, then none of these potential attacks could be performed. You actually need to be tuned in for it to actually be processing the data that's being provided on that radio station.
I see.
So if you're ultra paranoid, you could just keep your DAB radio turned off.
Well, I always have mine off anyway. I never listen to radio.
Okay.
So, okay, so it's actually built in all the new cars, what you're saying. And so you still use your car, even with DAB disabled, right?
Yeah.
You can still drive it and everything.
Absolutely, yeah.
And your braking system and all that would still work. That's good.
Yeah.
In one of your first slides, you mentioned that DAB could be used as a carrier for Java. Got mentioned in there. So
Yeah.
the receivers actually have a JVM.
Sorry.
Can they actually run the Java code that you would?
I haven't actually found an implementation of that yet. That's in the actual specification. So one of the types of the multimedia object transfer data types, you have to specify it in the protocol. One of those types is Java, but I've never seen it actually used in the wild.
Well, thank God for that. And the next question is, okay, so you could send down some sort of website that presumably would have, I don't know, maybe the option of running JavaScript or something. Could that be used as a way to contact or connect to the dbus server? So as you mentioned, often dbus is open, connected to all interfaces.
Yeah.
We can see that changing, like in the Chrysler update, I think fixes that.
Yeah.
But if you have code running on the head unit, then it's going to be able to talk back to localhost.
Yeah.
So would that be an attack vector then? Download a web page that has then a link back into localhost?
Yeah, certainly. I mean, if you've got code running on the head unit itself, then you're going to be able to talk to those dbus interfaces if they're then talking onto CAN. There are ways of authenticating dbus.
Yeah.
However, it's user-based, and if you are running at the user level that runs the whole infotainment system, it's probably going to be root. So it's going to be game over anyway. So.
Great, thank you.
I haven't looked at satellite radio. No.
Okay, thanks for the presentation, very interesting. You built nice tools for fuzzing. Did your fuzzing result in any crashing or anything on the existing units you tested or on the software decoders?
I have identified some vulnerabilities, and those have been communicated to the various vendors. I haven't done a thorough investigation of all the different head units from different OEMs. We're currently in the process of setting up an infotainment test lab at NCC Group. So we're going to have a lot more head units to test. So hopefully in future I'll be able to provide a lot more information about how widespread vulnerabilities in DAB are.
Okay, thanks.
Hello? Hi. So could you explain how would you debug the crash on the head unit? Like, is there like a port you can interact with?
Sure. I mean, it depends on the operating system that's running on the head unit. There's lots and lots of different ones that are used, from QNX to Linux to kind of more proprietary operating systems that are running. What we tend to do to try and root cause the bugs is we'll use kind of conventional hardware reverse engineering processes. So we'll look for JTAG interfaces, we'll look for UARTs, anything that might provide us with debug information about what's going on with the crashes. But yeah, it's a kind of case-by-case basis depending on the OS and depending on the infotainment system in question.
Okay, one more question. So earlier you mentioned that you use a physical wire to do the interaction instead of sending it over the air.
Yeah.
Could you kind of explain about the wire, like the specification or where we can get that to play with?
It's literally just a piece of coaxial cable. So it's like the cable that connects to your antenna. There's nothing special about the cable. It's just connecting via it's got an attenuator connected. It's like 60 dB attenuator, so it really reduces the signal level, and that then connects to the cable, which connects directly to the receiver. And it's literally emulating the signal path over RF, but we're not breaking the law because we're not transmitting wirelessly.
Thank you.
Thanks. Thanks very much.